Welcome to Lecture 2, Science and Agronomy Part 2. This is part of Agronomy 2 ALM210 subject, which is part of the agricultural degree offered at North Melbourne Institute of TAFE, based in Australia. Please visit our website for further details on the subject, courses and educational products that we offer. My name is Dr. Nikki Cooley. Please ensure that you have watched Part 1, Science and Agronomy, before completing this lecture. It is also advisable that you watch the Yang Ying Teaching and Research Demonstrator. This is provided on Moodle under this section. In the second part of this lecture, we will examine the Yang Ying Teaching and Research Demonstrator in further details. This teaching aid is separated into two parts. There is a research field experimentation part and a cropping and fertilizer demonstration part. This lecture will be separated into two sections. We will start looking at the research field experimentation, where we will explore the background, hypothesis, treatments, setup, inputs and replication. Then we will go on to describe a demonstrator and the components that make up a demonstrator. We will show you how you set up this demonstrator, and there will be a number of tasks that we will require you to complete this lecture notes. Please ensure, where possible, you watch this lecture before coming to the Yang Ying farm. The Yang Ying Teaching and Research Demonstrator is based across two paddocks at the Yang Ying farm, which is owned by NMIT. We have two aims with this teaching and research demonstrator. The first is to introduce the concept of a demonstrator. This is where an area or section of land on a farm shows or illustrates some form of management or new variety. Our demonstrator is going to show several different species and the effect of adding strips of fertilizer to these species. I have called this the cropping and fertilizer demonstrator. The second concept is that of the scientific method. This is agronomical science in action. A number of experiments have been set up in this paddock to demonstrate the scientific method. We will start by describing the research in this demonstrator, and then the last part of this lecture will concentrate on the cropping and fertilizer demonstrator. The research part, where the experiments will be shown, are located in Paddock 5. Let us start with a bit about the background. Why are we setting up these experiments and what do we hope to achieve? So let us start with a bit of a background. What was the problem we were trying to address with the research and teaching demonstrator? Nitrogen is very important to cereal crop growth and development. Nitrogen in cereal crops is attained principally from the soil organic matter breakdown and the addition of fertilizer. Australia is subject to climate variation, and winter cropping is common practice in Australia. The evolution of this cropping time has been a result of reasonably reliable winter rainfall, with favourable temperatures that have resulted in an established pathway to market. Australia is subject to significant seasonal climatic variation, which can impact on rainfall reliability. In seasons where rainfall is low, plant growth and development has been negatively impacted, with specific impacts to yield. So to summarise this problem, when we have low rainfall in the winter, Australian cropping is impacted. It is assumed that the inability for the plant to access nitrogen during this low rainfall is contributing to the low yield. So let us have a think about some possible solutions. There are indeed several. The first and probably most obvious is if this occurs in low rainfall seasons, then you could increase the amount of water available to the crops, which would aid the nitrogen uptake. It turns out practically this is very difficult to do in many cropping environments. You require additional infrastructure. You need a water source, and both of these will incur significant costs. The increased productivity will not match the increased costs. Therefore, this is not a viable solution as we grow crops for a commodity. Another solution is to use a product such as a nitrogen fertilizer that can be readily available and absorbed by crop roots effectively in low rainfall seasons. If this product was effective, this would minimize the impact on the crop development and yield. In theory, such application could improve crop productivity. So, in conclusion, if the extra profit gained was greater than the cost of this product, and remember that you have to include any infrastructure and application costs, this would increase returns. So from the background and from a possible solution identified, you will see that we have entered into a number of disciplines. We have to have an understanding of the economics of this solution. Clearly, the soil environment is very important. The physiology of the plant and how it responds to both the soil and the climate are important, and an understanding of our climate and climate variability in Australia. Once you have a problem and a potential solution that you'd like to test, the next stage is to compile an aim. We may compile the following aim for our particular situation: to demonstrate that the application of the product green urea to fodder wheat will significantly improve crop growth, development and yield. In order to convert this aim into a concept that we can test scientifically, we need to compile a null hypothesis. I would like you to attempt to compile a null hypothesis for this experimental aim. Please bring this along to the next practical day at Yang Ying Farm. We will discuss all null hypotheses and compile the best null hypotheses and put it up on Moodle. Please note you will need the null hypothesis included for you to complete your lecture notes for this topic. It is worth noting for consideration that suboptimal nitrogen uptake is most prevalent in low rainfall seasons. This means there is probably an interesting relationship between soil moisture, water availability, and plant nitrogen uptake. It is worth noting that soil moisture is a very important parameter to collect observations on when conducting our kind of experiments. Also, in an ideal world, you would set up controlled environmental experiments alongside. This would allow you to control soil moisture and temperature and other climatic inputs while adjusting your green urea concentrations. The next stage of the plan is to design an experiment to test the null hypothesis that you have created. There are, in fact, several feasible methods. You could develop a model and test the model. Usually this kind of modelling requires some observed data. You can set up a field trial, as we have been discussing with the Yang Ying teaching and research demonstrator, or you can set up controlled environmental trials. This is where you may have your wheat plants growing in pots in an environment where you can control such climatic inputs as the temperature, soil moisture, humidity, wind. As I said at the beginning of this slide, all of these methods are feasible. They all come with their own advantages and disadvantages. The advantage of modelling, once you set up your calibration correctly, is that you can take and test this hypothesis in a number of climates or in a number of different conditions. The disadvantage of modelling is that the number of inputs that occur on a farm, it's not just climate, management, environment, etc., are so large that it is difficult to construct a model that enables you to account for all of these inputs. Field trials, as we are conducting at the Yangying Teaching and Research Demonstrator, are considered often the most favourable. They allow you to test your hypothesis in the environment, climate, soil, management practice, etc., where you hope to use the product. The disadvantages of field trials are that they take time, money, and resources. For field trials observations to be truly robust, you have to have at least 5 years of data. Controlled environmental trials are very useful for establishing the hypothetical and ideal scenarios. These are often where you might look at concepts such as mode of action. The other significant advantage of conducting a field trial, an environmentally controlled trial, is that we can test plant available water against the increasing urea concentrations. This would give us a very good understanding of what was going on and what we could possibly apply to our climate, environment, and soil type. For the concepts of this subject, we will be doing 2 things. We will be conducting a field trial looking at these problems, and secondly, we will be doing some modelling. This will enable you to have a complete approach and understanding about the advantages and disadvantages of both of these methods. In the Yangying Teaching and Research Demonstrator, there are 2 aspects which we consider with respect to this experiment. The first one is, does the application of green urea improve crop productivity? In this case, we would apply the product and compare it with a control or a number of controls. I'd like you to take some time now to pause this lecture and have a think about what that control or controls might be. Ensure that you write these and your ideas in your lecture notes and bring them to the Yangying Field Day visit. We will be discussing these potential controls at length during your visit. The second very important aspect that we have to consider with such an experiment is what is the best concentration or application rate of the product we are going to test, the green urea. Principally, the application rate is suggested by the company that produces the product. This is called a recommended rate. This would be the application rate that we use in the first experiment. However, is this application rate or recommended rate optimal for our crop, our cropping system, climate, soil and environment? Different concentrations of different cropping chemicals can change optimal responses. You need to be aware of the management practices you are using, the growing stage at which you apply the chemical, and the soil moisture. There are other factors not considered here, which we will talk about later. There are well-articulated methods for investigating the best concentration of a chemical product on a crop. These experiments allow you to produce what is called a response curve. That is, as you increase the concentration of the product, in our case the fertilizer, how does the growth of the crop respond with each incremental increase? These kinds of experiments are very useful when assessing the best concentration to use in your farming system. Ideally, the grower would have at least 5 concentrations to investigate. For example, you may start off with 0, 20, 40, 60 and 80 grams per litre, and at least 3 replicates at each concentration. As you can begin to see, this is a lot of work as it requires many plots. A plot is an area of land that has one treatment at one concentration. Experimentation conducted in field environments often requires some experimental preparation before the experiment can start. In our situation on paddock 5, before the experiment started, we had a pasture mix. This had been down for several years. Cattle had grazed occasionally on this pasture mix. We identified that we needed to control the bent grass, as this is now in a situation of being termed as a weed. Before spraying the bent grass and the other weeds in this paddock, we allowed sheep to graze in the paddock for several weeks to reduce the growth of the grasses. This makes the application of the chemical herbicide more effective. We applied trifluran spray onto paddock 5 at the end of March in 2013. When conducting trials in fields, there are a number of approaches that you can use. You can use entire fields and compare them, or you can separate the fields into blocks or smaller units of land where you conduct your experiment. In paddock 5 at the Yangying Teaching and Research Demonstrator, the total paddock size was 3.4 hectares. We determined that the potential experimental area that was available for use was 2.7 hectares. This was the area for both experiments. We turned over the paddock after the spraying of the weeds to ensure that it was ready for the sowing of our new crop. This was all part of the setup. Other components of the setup was that we had to design the plots and the block layout for this experiment. In an ideal world, you make the assumption that there is no variability in your soil. This, however, is rarely true. Therefore, we conducted pre-experimental soil testing to determine the soil variability in this paddock. During these tests, we were able to identify the type, texture of the soil pH, and we sent some soil analysis off for nutrient composition. Therefore, before the experiment, we could determine if there were any nutrients that were lacking in this soil. The image on the slide is from Experiment 1 Paddock 5, and it shows you the location of the soil tests. These locations were determined via GPS, and they were then added to this Google Earth map. You will see on the right hand side the Plenty Road, and this will enable you to determine orientation when you're at the Yangying site. This slide shows the results of soil test from Paddock 5. Please take some time to look at these results. We will be discussing them when we are at the Yangying farm. When you are conducting fertilizer trials, the plot design is essential. You need to understand that some fertiles are labile or soluble in soils. During a heavy rain event, as the water in the soil increases, so will the movement of this water and any dissolved fertilizer. The movement tends to follow the contours of the land. In Paddock 5, there is a slight slope downhill towards Plenty Road. Therefore, we need to design plots that take into account this slope and movement of fertilizer. Plot designs must also take into account edge effects. There are many possible inputs that can cause edge effects, and this will depend on the location of the plot, the design of the plot, the resulting contours of the land, soil type and structure, and climate. The most common inputs are different wind conditions, that is, there is more wind at the edge of the plot, and different humidities. Plot design when conducting fertilizer application must consider root growth. On the slide you will see some examples of plot design. The outer area, or green area, is the fertilizer application area. The inner area is the area where the soil, crop and climate can be measured in order to assess the effect of the treatment. You will also observe that there are two designs on the slide. The arrows around these designs suggest where most of the soil-water movement occurs. The arrow on the left-hand side is suggesting that water will move up and down the field as well as across the field, while the image on the right-hand side of the plot suggests that water movement is only down the field. This is the second one on the right-hand side of the image is the design that we have implemented in the yin-yang, as due to the topography of the field, we can be assured that water will travel down and not across or up our experimental plots. Once our plot design is completed, we then move on to the block design. There are many different combinations of block and plot designs depending on what statistical assumptions that you make. In our experiment, we have done soil tests and concluded that the soil structure does not differ significantly within the area we have selected within our paddock. Therefore, we are confident that a random blocked design would be ideal to best represent both our physical aspects of the trial, our plant growth, the assumptions behind this experimentation, and will support their statistics. Each plot in our block will contain a different treatment. The order of the plots will be random. The area of the blocks are situated in will also be determined randomly. I have drawn a simple illustration of each plot in our block. A random number generator will be used to assign the treatments. In an ideal experimentation, you would insert row spaces between each plot. In our experience for fertilizer experiments, 2 row spacings are ideal. This does, however, depend on the direction of the rows relative to the layout of the plots. At your next visit at Yanyin, name the row orientation. Is it north-south or east-west? And if this is different, update this illustration to complete your notes. Now let us take a few slides to think about fertilizing and nitrogen. Nitrogen sources. Many crop species require nitrogen release from decomposition of soil organic matter or nitrogen supplied by some form of fixation. For example, the crop legumes can meet their nitrogen requirements through nitrogen fixation. Terrestrial plants take up nitrogen mostly as the compound nitrate, NO3, and to a lesser extent ammonium, where the nitrogen is provided by organic forms, fertilizers, or directly from the atmospheric fixation. I'd like to compare a number of fertilizers. The first one is granulated monoaminophosphate, or MAP fertilizer. It contains 10% nitrogen, 21.9% phosphate, and 1.5% sulfur. Also available is the product urea. This only contains nitrogen at 46%. It is regarded as a concentrated nitrogen fertilizer, mainly used for pre-plant application of grain crops and for side or top dressing pasture and foliage crops, grain, cotton, vegetables and sugarcane. Another product is shortened to DAP, which stands for granulated diammonium phosphate fertilizer. This contains 18% nitrogen, 20% phosphate and 1.6% sulfate. It is mainly used at planting in grain and forage crops, but also in sugarcane and for top dressing pastures. All 3 products are commonly used in agronomy. You will note that there are different concentrations of nitrogen, different effectiveness of nitrogen uptake, different stages and crop types that these products are recommended for. Two of the products, MAP and DAP, contain other nutrients, while urea does not contain any other nutrients. It is important that you become familiar with these products, as they are very important in agriculture and agronomy. Urea and green urea are forms of nitrogen. Urea is an organic compound which can be used as a nitrogen fertilizer in cropping. The chemical formula is CONH2, where C are carbon atoms, O is oxygen, N is nitrogen, and H is hydrogen. The chemical formula is shown on the left-hand side of the slide. When you describe chemically urea, you would say that NH2 groups are joined by a carbonyl group, COO bond O. It is a colourless, odourless solid, highly soluble in water, and very low toxicity. Dissolved in water is neither acidic nor alkaline. Green urea is another fertiliser available commercially. It is urea that has been treated with a urease inhibitor. This inhibitor is N-butyl thiophosphoric triamide, or NBPT. The added compound delays hydrolysis of urea into nitrogen forms that may be lost to the atmosphere. It is recommended that top dressing where volatilization loss of ammonia in the atmosphere is likely to occur. Such products as green urea 7 can limit volatilization losses for up to 7 days, while green urea 14 offers protection up to 14 days. The commercial claims are that it boosts yields while improving fertilizer use and efficiency compared to the product urea. Incitec Pivot is an example of a commercial provider of green urea. Please note this is not an endorsement for this particular product, just an example of this product. The breakdown of urea is by a process known as hydrolysis. When hydrolysis occurs, it leads to the production of ammonia, NH3, which is a gas, or ammonium, NH4. Both of these compounds are plant nutrients. When the urea is top dressed, that means when it's added to the surface of the soil, ammonia, NH3, can be lost to the atmosphere. This means the nitrogen does not reach the plant roots and results in both a lower nitrogen efficiency and additional financial costs. The amount of NH3 that is lost from the site will depend upon many factors. One of these factors is crop type, i.e. do you have pasture, bare cropping soil, trash blanketed systems, etc. The differences are due to the differences in the rate of NH3 loss, and this largely depends on how quickly urea is broken down. The degradation rate of urea depends on the amount of activity of an enzyme called urease, which is found in organic materials. Different crops and pasture systems contain different amounts of urease. For example, a dairy pasture has high risk of NH3 loss. Soil pH is another factor that will change the NH3 loss. If you have a greater pH, that means more alkaline soils, this will influence whether the gas NH3 or the plant nutrient NH4+ is produced. The NH3 is lost to the atmosphere while NH4+ is not. The climate is another factor. Windy days have greater loss than still days. When the rain falls greater than 10 millimeters, urea is washed into the soil and so less NH3 is lost to the atmosphere. One of the ways of minimizing the risk of NH3 loss is to apply urease inhibitor to your urea. This slows the activity of the urease enzymes and so slows the rate of urea breakdown, and thus this is where the product green urea has stemmed from. I'd like you to stop this lecture at this point and go to the following video on the mode of action of green urea. This puts the concepts that we have been discussing into a visualization. The link for this HTTP video will be found on Moodle. In Experiment 1, Paddock 5, the recommended commercial rate for the application of urea and green urea was 55 kilograms. This was based on a 30 square metre trial area and the end product trial area of 140 metres by 80 metres or smaller plots. You should now have detailed knowledge of the setup and experimentation being conducted in Paddock 5. We will now learn about the demonstrator. The aim of this demonstrator is to show cropping and fertiliser. It is located in Paddock 7. An agronomical demonstrator is an area of the farm that shows the effects of an agronomical input, such as a management treatment or a new variety. Demonstrators are normally conducted by government R&D extension agencies, funding bodies, education facilities such as NMIT, cropping groups, and commercial companies. It should be noted that when a commercial company is demonstrating a product, they are trying to sell the product. Our demonstrator hopes to show the following: various crop varieties. We hope to show you what different crop varieties look like, and when you have a comparison which is many together and next to each other, it makes the differences and the similarities of these crops much easier to identify. You will also have learned from Agronomy 1 that climate and climate inputs are very important in crop growth. One can assume for the purpose of this demonstrator that the ambient climate across the field is equal. Therefore, with equal climate, how do each of these varieties' growth and yield change? We will be able to compare the phenological stages of many of these crops as they were sown about the same time, but you will see some are far more developed than others. The second object that we hope to show is the application of fertilizers. We have selected areas of the paddock and added urea, green urea and potassium. We are not hoping to make any scientific statements about these products. We are doing this in Paddock 5. But we are able to see the differences in these applications between the different crops. We will be able to demonstrate various weeds, pests and diseases. You will be able to see a variety-disease relationship. That is, that wheat may have one disease while the canola will not have that disease. Concepts will be talked about in this demonstrator. The field is an ecosystem, and this is something that you will be able to see from such a demonstrator. We will also be able to show spatial variation of soil and crop growth. I have called the demonstrator a cropping and fertiliser demonstrator, as principally we will demonstrate a number of different crops, demonstrate the response of green N, and demonstrate the response of potassium. I'm going to show you the design in the next few slides of the Paddock 7 demonstrator. Remember that we are not conducting scientific trials and we are not testing hypotheses, so there are no plots or blocks or replication. The purpose of this paddock is to demonstrate different crops and how they respond to the same soil type and same climatic environment. When managing a crop, you have to manage for the crop's optimal commodity. This can be different for different crops. Some crops are grown for fodder, while others might be grown for their protein content in their seed. Therefore, management practices in this demonstrator are not uniform. We started the cropping and fertiliser demonstrator by putting together a concept. The first thing we did was to ascertain simple facts like the total area of the paddock, the direction of north. We then identified components of our infrastructure and how this may impact on our site development. You have to consider such things of how do you sow the different seeds. Each piece of equipment that you have on your farm will have a different sowing depth and sowing width. We have divided our strips where we place our different crops by the width of our sower. We have left on the right hand side of the paddock the existing pasture. This will enable you to compare what the pasture was before we removed this and added the different varieties. We then conceptualized a number of different treatments, for example the addition of green urea and potassium. We assigned strips across the paddock. This will allow all treatments to be exposed to the different varieties. So that was the concept. Here is what we actually ended up with. You will see there are different strips and we had to do different initial treatments. Only wheat, barley, canola and chicory could be sprayed with pre-emergent herbicide, of which we use a product called triflufan at 2.5 litres per hectare. We do not spray oats, tonic plantain, new tetea, or the SPS sheep beef 600, which is a mixture, and the pre-emergent herbicide. We added fertilizer DAP at sowing, and you can see the previous slides in this presentation for details about DAP and what it is. Each plot size was 10.5 metres by 165 metres long. The next couple of slides are pictures of the Paddock 7, the Yang Ying demonstrator, when it was being set up. The picture on the left hand side is the land immediately after seeding, and the picture on the right hand side is the crop emerging. Can you identify what this crop is from this image? And can you identify the growing stage? Bring your answers to the first or second trip to Yang Ying and we will discuss them and compare them to where the growth is now. These images were taken on the 30th of April 2013. Here is the second crop I'd like you to try and identify. On the left hand side is a picture taken from far away showing the crop strip. On the right hand side is a close-up of this particular crop. There are 3 tasks I'd like you to complete. Task 1, identify the crop. Task 2, identify the growing stage. And task 3, can you tell me if this crop is a dicot or a monocot? Please bring your answers to the first and second trip to Yang Ying. If you are unsure what a dicot or a monocot is, then please take the time to find out and bring your answers to the next visit to Yang Ying and we will discuss. You will be able to compare the growing stage in this image, which was taken on the 30th of April 2013, with the current growing stage. Some of the details of the preparation of Paddock 7 are on the slide. On the 21st of March, the product glycophosphate cosidate, or Roundup Power Max, which is its commercial name, was added to both paddocks. It was added at a rate of 2 litres per hectare. The commercial product is supplied at 540 grams per litre. Note, only the cereals, canola and chicory were sprayed with the pre-emergent herbicide triflufan. We did not spray the tonics, the new tetea or SPS sheep beef 600 mix with the pre-emergent herbicide. We were aware that when you convert pastures to cereal crops, i.e. when you take the pasture that's existing in paddock 7, you remove it and you plant canola, there is a good chance that the existing snail and slug population could explode and have a significant negative consequences on our cereal crops. Therefore, on the 30th of March, assessment of slug and snails were conducted by the vet group. These pests are common in the pastures, and preventative methods were implemented to reduce their numbers. There are always issues when you change the content of a field. Ideally, we would have made the preparations for our demonstrator back in September last year, but this was not the case. We made the decision to go ahead with the demonstrator this year in early March. So we do not have ideal establishment time, and we have not been able to get rid of all the weeds and pests and diseases that we hoped. However, for the purpose of education, we can use this disadvantage as an advantage to learn about these effects and to learn about different pests and diseases. We will discuss this in more detail in our visit to the Yang Ying demonstrator. This slide contains details about the fertilizer application on the cropping and fertilizer demonstrator paddock 7. Total urea and green urea for paddock 7 is 132 kilograms. This is at a rate of 60 kilograms per hectare of nitrogen. The amount of MOP needed is 61 kilograms. This is at a rate of 60 kilograms of potassium per hectare. This is assuming that we have plot sizes of about 13 meters wide and 50 meters long, and a 10 meter strip of potassium at the bottom of each plot. As both paddocks were pasture before crops were added, and in paddock preparation these paddocks were ploughed, removing of most of the existing pasture, there is a good chance that N mineralization has occurred. Therefore, the commercial supplier of the green urea suggested that we go higher rather than lower in our rates. This is the reason as well why we increase the rate of potassium to 60 kilograms per hectare. The image on the slide is a flow chart which is bringing together the main points and objectives of the Yang Ying teaching and research demonstrator. Essentially, we are trying to demonstrate two different approaches. The first is a true demonstrator. It is quite different from a scientific trial. We are looking at fertilizer management in different crops. This is located in paddock 7. We have different crops selected, and we have applied strips across all of those crops of urea, green urea, and potassium. There has been no replication of this, and we are not trying to prove a hypothesis. We're just demonstrating what these components may or may not look like. While paddock 5 is a research trial. That is, we are trying to compare the use of rhere and green rhere on our wheat fodder crop. We are hoping to demonstrate the scientific method and enabling you a comparison between a demonstration of a scientific method and an industry-based demonstrator. Important facts to note: in this lecture we have covered the aim and the background and some of the knowledge already known. From this we have developed a null hypothesis. Once we have obtained the aims, background and null hypotheses, we can then select the most appropriate experimental methodology. In this case, a field trial in the paddocks. We have gone through the stages of a field trial setup, including block design, plot design, replication. We have selected our fodder wheat, and our fertilizers that we have investigated are urea and the product green urea. We are choosing to do these investigations by two experiments. The first experiment allows a comparison of the commercial rate of urea against the commercial rate of green urea. The second experiment allows us to ask the question, what is the best rate for our crop in our climate on our soils? Please take some time to familiarise yourself with the layout and the differences between Paddock 5, the research demonstrator, and Paddock 7, the teaching demonstrator. We will be using this resource extensively throughout this subject this semester. You will be doing several practicals. These will help apply some of the concepts that we will be teaching in this subject, and do include such topics as fertilizer, growth, application of the scientific method, being able to identify both different crops and weeds, weed management, and the use of chemicals. So to summarise all the things that we have covered in this lecture, we have explored the scientific method and agronomy. We have become familiar with the scientific methods that you can use, modelling versus observed data from field experiment data, traditional methods versus new approaches. Please remember that Tutorial 1 completes these lecture notes. We have covered in some depth the experimentation at Yangying Teaching and Research Demonstrator, an important resource for your studies. Please note, to complete these lecture notes, you will need to complete the tasks and add additional information that you will receive from your Yangying farm visit. Your lecture notes are not complete without these inputs.